Okay, so what we are trying is to go into the steps how the elimination reactions using a geminal dihalide proceeds to prepare our alkynes. No? So initially we have our
Excuse me, ma'am. Wala pa
yes.
naka-share ang screen.
Ha? Wala na
Wala pa
share.
naka-share.
Okay. So again, we are trying to prepare our alkynes now using the elimination reaction. Our starting material is a geminal dichloride. So the steps actually is just the same with using a vicinal dihalides, no? But so we have our vicinal geminal dihalides rather. Klaro on screen. Maklaro?
Yes, ma'am. Clara.
Okay, so what you will have is the same step, no, with the vicinal dihalide. So you have your base that will abstract a proton, and once the proton is abstracted, no, it will leave with its electron pair sa carbon-carbon. So we will get a double bond here. Once the double bond is being formed, then the other halide will have to leave the substrate. So our product is just this. Okay, let's copy. So since mo-leave man siya, okay, you have your protons here. Okay, and then what will happen is that you will have a double bond, right? You have another Cl here, and you have a double bond. So you have okay, once the proton is abstracted, we get our double bond here. Okay, once the double bond is formed, mawala na ang chlorine. No? Bringing with it its plus Cl. Plus Cl with that Cl. Of course, there is 1, 2, 3, 4, 5, 6, 7, 8 node charge negative. It will be for chlorine. Of course, this one, chlorine, each chlorine atom is surrounded with 6 electrons. So delete na rin electrons na if you get confused. And it will be the charge, and you will get your alkene here with a double bond and a chloride. Okay. So once you have this one, this becomes our starting material to our next step. Okay, so you have your amide again that will okay, so you have your amide. Para magkaroon double bond, draw the hydrogens. Okay, so you can abstract this. Okay, once the proton is subtracted, then we'll use this to form a bond. I should use a different color. Okay, so abstract the proton. Once the proton is abstracted, then the electrons from the bond will go to carbon to form a triple bond. And once a triple bond is formed, then the chlorine will have to leave. Okay, and you'll get your product, which is a triple bond. See. And you have your C, and then you have C, okay. It's a triple bond, so dapat so you have 1, 2, 3. Hindi naman ka carbon. Dapat hydrogens. So you have this one carbon here, and then one carbon and another carbon. So that's 1, 2, 2 carbons, and carbon here is attached to hydrogen. Okay, so you have your product. This one, CH, CH. So it's the same way of how you prepare actually from your vicinal, like okay, so if for example you get lost, know how you are stuck, like you don't know what you don't know how the reaction proceed. So you always have to use your arrows, you always have to find your electrons, your base, or will it be which atom will it attack, so that you can have an idea what will be your product. Okay, so you can practice on this one, 7.21, that will be practice. So terminal alkynes can also be converted to nucleophiles for carbon-carbon bond formation. So for example, you have your acetylenic proton in ethine here. For any terminal alkyne, you remember the pK is around 25 and it's very acidic. It can be removed with a strong base. Okay, if you remember earlier in one of the reactions, you have this and we actually have another NH2. What will happen is that you have an NH2, no, it will actually obstruct the proton sa imong alkyne here. So this is what we are saying here, that any acetylenic proton of ethine can be removed with a strong base such as in sodium 8. So the result is your alkynide anion. You have a triple bond and a a carbon and ion here. The carbon having an electrons with a negative charge. So another acetylenic proton you have here and an amide in the presence of liquid ammonia you have here. And you can actually revert this one to this. If we protonate this again, we react this one with NH4Cl. Now the NH4 plus, the proton from NH4 plus can be used to be donated with this. This one can obstruct the, say this one, so it will actually, the electrons here will be used to obstruct the H from NH4 plus, this one here, and you actually get your C carbon hydrogen bond, and you will, if the proton from NH4 plus is removed, you actually have produced your NH3 and you have your Cls eliminated. Okay, so I hope it's clear with you. You have this one. So again, if ever you are stuck with this one, always remember that you can recover your protonated alkyne with acidification. No. Okay, so the following are general alkynide and ions are useful nucleophiles for carbon-carbon bond forming reactions with primary alkyl halides or other primary substrate. So there are useful nucleophiles or actually a base, especially if we react this one with an acid. They are useful nucleophiles also for carbon-carbon bond formation reactions with primary alkyl halides or other primary substrates. So example, saan niya paggamit? How is it being useful as a nucleophile, no, when we are dealing with primary alkyl halides. So let's say you have a primary alkyl halides. Now this can act as a nucleophile. If you have your carbon attached to a halide, then this carbon becomes partially positive. So you can actually attack this carbon here to form a bond, triple bond carbon C bonds, and you will have your leaving group leave the substrate here. So your alkynide can actually also act as a nucleophile. Example, specific example rather. So you have your CH3, CH2, your ethynyl bromide. How do you say this one? You have your ethyl bromide rather, ethyl bromide, and you have your 1, 2, 3, 4 butanide. No, it will be used as a nucleophile to attack this carbon here. So you have your triple bond C and you have your CH2, CH3 here. So you have increased the length of your hexane in this case. So again, this is an example of using your alkynide as a nucleophile. Alkynide used this is an example also of substitution reaction. So this is the general validation. So you have a 1 degree alkyl halide and you have your alkynide can easily attack this one via the SN2 reaction here. Primary alkyl halide should be used in the alkylation of alkynide ions so as to avoid competition by elimination. So we don't want this to proceed with the competition reaction via elimination. So remember, as a nucleophile, it can also obstruct a base. But if we are using a 1 degree alkyl halide, it will proceed to substitution reaction via SN. So if you want to proceed with the substitution reaction, let's say, for example, you want to increase the alkyl, the number of carbons blend for containing your triple bond, then you can use the substitution reaction. Otherwise, it can act as a base to form your alkene you have here. No? So for example, use of secondary or tertiary substrate causes the E2 elimination instead of substitution. So here in this case, it will obstruct the proton. Now this is a secondary alkyl halide. You have a CBr, but you have another R attached to this carbon. So this is a 2 degree alkyl halide. So in this case, it will become a competing reaction. The elimination reaction will become a competing reaction to proceed for substitution. So instead of simply having this kind of product, increasing the chain length, you will have supposedly your RC, triple bond C, and C. See this one, no? What you will get also is product for the E2 reaction. So you have, once this obstructs the proton, you will get the bond from this will be used to form a double bond here. And once you get this double bond here, PR will leave. And you will get your R prime CH, this one, and CHR double bond prime. R, a CR double prime here, CH. You'll get this product and eliminating your group. So then you will recover your alkyne, automated alkyne. Okay, so again, for alkynide to proceed substitution reaction, we have to use a 1 degree alkyl halide. Otherwise, if we use a 2 degree alkyl halide, there is competing reaction that will proceed to eliminate elimination reaction. So outline the synthesis of 4-phenyl 2-butene from 1-propyne. Outline a synthesis of 4-phenyl 2-butene from 1-propyne. So this is our starting material. Okay, and then you will have to use your 4-phenyl 2-butene. The first step for you is to write on the structure of your product. Now, you couldn't imagine that would be your materials to use if you don't know the structure of our product. Okay, so first, write on the structure of 4-phenyl 2-butene. You have your 4-phenyl 2-butene, C6H5, so you have 1, 2, 3, 4. Okay, and this is your structure. This is your product, and this is your starting material. So you can imagine how to do that one. So you have your CH3 here, CH3, triple bond hydrogen here, and you have your CH, you have your carbon here, and you have your C6H5. So imagine asa siya na sabay, you have here. Somewhere here is where the bond, this one, this, and this is where the bond is being formed. So how did it happen? So it looks like there is can proceed with a substitution reaction. Remember earlier I've said that for the substitution reaction, you can actually increase on the chain length, no? Having your triple bond. So here it looks like it proceeds the substitution reaction. So for this to proceed with substitution reaction, we first have to eliminate this one to produce our alkynide. Now you should have your triple bond, CC, and negative one. So how to remove this? We have to remove this one with a base. Remember this. Okay, we have to have a base to produce this one. Once you produce your triple bond, see that negative, your alkynide, no, then you can attack a primary alkyl halide to increase our chain length. Okay, so anyone who can share your answer? Simply lang, no, you have the one that I've said, you abstract this proton here with your amide, you get your alkynide ion. Once you have your alkynide ion, you can have your CH2, C6H5 with a bromide here. Okay, CH2, C6H5. The C6H5 is simply your phenyl group, no, benzene katong a ring with a cyclic inside. So that's your benzene bromide. And once you have this, you can actually do this is a 1 degree alkyl halide because the bromine is connected to CH2, primary carbon. It's not connected to the ring. So this is an alkyl bromide primary, and it can proceed with substitution reaction via the SN2 mechanism. And you get your product. Okay, so the easiest way for you to proceed with the reaction is you have to think the structure, the starting material, the structure of the product. No? So you can imagine what will be the necessary materials you will have to add or the steps you have to undertake in order to produce your product. Next problem, your goal is to synthesize 4,4-dimethylpentane. You have a choice of beginning with any of the following. 4,4-dimethylpentane. You have the choice, so you have to draw this one. Pentane, so you have your triple bond, no, on the second carbon. And then on the fourth carbon, you have 4 dimethylene. Okay, you have a choice of beginning with any of the following reagents. Assume that you all have available sodium amide and liquid ammonia. So this will be your base, sodium amide and liquid ammonia. Outline the best synthesis of the required compound. Okay, so if you have your this one to be your starting material, if you have this as your starting material, you can use your base, your amide to abstract this proton. You have your alkynide here. If your alkynide here can actually, this is a tertiary alkyl halide. Okay, so it's not easy to attack this one to produce your 1, 2, 3, 4, 5. No? So if you have this 1, 2, 3, 4, 5, it's not easy to have this, to use this one. So what you have to do is you can also use this one, because you can once you produce your alkynide here, then you can do the substitution reaction with the alkyl bromide, no, to produce this one. So pag nagsumpay na siya, you actually obtain your product for 4-dimethylpentane. I hope you're following me. So you have 1, 2, 3, 4, 5. So in carbon 2, you have a triple bond. If this is our sumpay siya, you will get your carbon 4 having a double bond, CH3, CH3, and CH3. Okay. But the thing is, if we start to this one, to have this one, it's not possible because this is the tertiary alkyl bromide. Okay, so it's not possible to use this and this as your starting material. You can try this one. 1, 2, 3, 4. This is already 4 carbon. You need to have 2 methylpentanes at 5. Your final product should have 5 carbons. We start this one. And you can abstract this as a base. Once you abstract this one as a base, your base amide, then you get your alkynide. Once you get your alkynide, then you can do substitution reaction with an alkyl halide here, which is primary. So once you get your alkyl halide here, you can do substitution reactions. You get C, triple bond C, and you get your CH3. Okay, so you sumpay na siya, and then you can siya ma-eliminate CIUD. So you practice on that. I have already explained how to do that one. Why the first two it's not feasible, why second is possible. Okay, 7.14 general principles of structures and reactivity illustrated by the alkylation of alkynide ions. Okay, so let's have the reactivity of the alkylation of the alkynide ions. Remember, we have the alkynide ion now prepared via the acid-base reaction. You have your base obstructing the proton. The preparation of the alkynide ion involves simple Bronsted-Lowry acid-base reaction. As you have seen in section 7. In the previous chapter 7, no, the hydrogen of a terminal alkyne is quickly acidic and with a strong base. Okay, I have already explained this one, balik-balik. Secondly, so since the proton in the alkyne, terminal alkyne is very acidic, you can actually prepare your alkynide ion. Once you form your alkynide ion, it can act as a Lewis base and with which the alkyl halide reacts as an electron pair acceptor. So your Lewis base can attack your Lewis acid, and thus the alkynide ion can be called a nucleophile. Okay, this is simply this one. It can act as a base. It uses its electron pair to attack this one. And since this is the one that accepts the electrons, your alkyl halide is also called your Lewis acid. Okay, so this number 2. Number 3, the alkyl halide can be called an electrophile. Okay, since it's partially positive, okay, an electrophile is the partial positive charge of the carbon bearing the halogen. It is our agent that seeks a negative charge. Okay, so I have already mentioned here. So since you have your carbon here attached to your halogen, halogen is more electronegative than carbon, so your halogen will bear partial negative charge and carbon will bear a partial positive charge. Okay, so since it contains a partial positive charge, this is what we call, aside from being called a Lewis acid, we also call this one as an electrophile. An electrophile is a carbon or is a species that contains a partial positive charge that always seeks a negative center. So it always seeks this one. A noctophile is a species that contains an electron with it, and it always seeks a positive center. So mag-partner that's noctophile of sa electrophile. So therefore, the alkyl halide is what we call as an electrophile. Okay, I have already explained why. See, alkyl halide is the electrophile because of the polarity in the alkyl halide bond. It's because of the difference in their electronegativity between the hydrogen and the carbon. The halogen will always be more electronegative than the carbon, so carbon will be left as a partial positive as you have here. No, if you have your alkyl halide, for example, your halogen will be is the one that is more electronegative, so it will bear the partial negative charge, and all the electron density now between this carbon and halide will be directed towards your halogen, so it will become partial negatively charged and carbon will become partial positive charge. Okay, so that's why I call this one to be an electrophile, and here your alkynide, consider this one as your nucleophile. Electrophile because it contains a positive center. And then you have this is the reaction of your alkynide, acetylide, an ion, and you have your chloromethane to follow the substitution reaction, and you get an alkyne here. Okay, so here is the electron density map of your species involved in the reaction. You see here that's very red for an alkynide. It's because it contains a lot of electrons here. There's a greater charge density on this carbon bearing a negative charge and then more electrons. Now let's proceed to the hydrogenation of alkanes. Now, one of the reactions of alkanes is the hydrogenation. So alkanes react with hydrogen in the presence of a variety of metal catalysts. So it's in a hydrogenation. So one of the reactions of alkene is the hydrohalogenation. So it reacts with hydrogen to obtain your alkane. Okay, so to do that, it actually uses catalysts like insoluble catalysts like palladium or nickel catalysts. Now, if we are using platinum, palladium, or nickel catalysts, we call this one as heterogeneous catalysis. Why? Because these are insoluble. Now, these are metals in powder form. So since they are not in the same phase, for example, your alkenes can be liquid or can be gas. So they are the same phase. They proceed via the heterogeneous catalysis in the presence of this species. So in the hydrohalogenation of alkanes, we have our species or reactants or agents, your hydrogen in the presence of catalysts, like your metal catalysts, like platinum, palladium, nickel, and usually at a high temperature, high pressure. We can also use a homogeneous catalyst, for example, your rhodium or ruthenium complexes, such as your Wilkinson's catalyst, like 3-triphenylphosphine rhodium chloride, this one, like this one. Okay, we call this one as a homogeneous catalyst. One because they are soluble in the solution in your reaction agent. Okay. So here what happens is the hydrogenation of alkanes. From a double bond, we can actually obtain our alkanes. Mawala ang double bond addition reaction. So we can use the hydrogenation of alkanes also we use with our unsaturated fats. For example, here is our unsaturated fats. You can see in oils and fats here. and react this with hydrogen in the presence of catalyst, we actually obtain our, from unsaturated, we obtain our saturated compounds. Okay, example, any reaction is, let's say, mag-prepare mo ka ng like sa margarine, no? We actually, this one is more solid than this one. So the saturated compounds are more solid than this one. So they are more organized than this. So hydrogenation of alkene is an exothermic reaction. The heat of reaction is usually around 1 to 20 kilojoules per mole. And what happens here is from CH, double bond CH, you know, you actually have your H2 distributed among the 2 carbon atoms bearing the double bond. You get 2 CH2, CH2. So the process is exothermic, and there is usually a high free energy of activation for uncatalyzed alkene. Usually, if there's no catalysts, there's actually a very high energy of activation. So this is the pink one with no catalyst. You have your product and you have your intermediate to produce your product here. Your single bond, your saturated compound here. There's actually a very high energy of activation. It's hard to proceed this because there is a lot of energy to climb to proceed with the transition state to form your product. So it's not very, the delta G is, this one is very, very large. No, this one is compared, if we use a catalyst like this one, the energy of activation actually is lower. Catalyst, and we proceed with a different intermediate products before we have our final product here. But you notice here in the blue that the free energy of activation is actually lower. And this is the reason that using the catalyst now, the reaction is much hastened and the delta G is much lower and it's more spontaneous as you compared with an uncatalyzed hydrogenation reaction process. So I have already mentioned the heterogeneous hydrogenation catalyst typically involves finely dissolved platinum, palladium, nickel, or rhodium deposited on the surface of carbon or charcoal. And we use hydrogen gas introduced into the atmosphere of the reaction. Vessels adsorbs to the metal by a chemical reaction. And then there is this collision of the alkene and the catalysts, no? This one, your palladium, nickel. And so collision of our reactants, alkene and our catalyst will cause the adsorption of the hydrogen gas to the alkene. And there is a stepwise reaction of alkene you have here. So what happens, this is the catalytic hydrogenation, which is a Synth addition. You see Synth, the reactants is being added on the same site, it's a Synth addition. So you have a surface metal catalyst, say in powdered form. So first is the hydrogen adsorption. So you have a metal catalyst and it will absorb the hydrogen to its surface. So once it absorbs the hydrogen to the surface, the second is that this in green, AB, will also absorb the alkene to its surface. So since the catalyst absorbs both the hydrogen and the alkene, it brings close contact between the alkene and the hydrogen. From a close contact, and the collision between hydrogen and this double bond is much increased now because they are in close contact via the surface of your catalysts, surface metal catalyst. So once you have that, it actually proceeds with the hydrogen added to your alkene both here, and the double bond actually is removed to produce your carbon hydrogen. It's a Synth addition, which means that the hydrogen is being added to the double bond on the same side. So CD here is a stepwise transfer of both hydrogen and atoms to the same phase so that can be the Synth addition. Okay, so an addition that places the parts of the adding reagent at the same side, we call that one as a Synth addition. Like say, for example, you have an XY and you have a double bond. When the XY, these two atoms are added in the same side to your reactant, no, call this one as a syn addition. When they are added on the opposite side, we call this one as an anti-addition. So we will learn in the next chapter 8 a number of important syn and anti-additions to both the alkenes and alkynes. So we'll learn more of that in chapter 8. So we'll first have an example for the alkynes. Aside from alkenes, the alkynes also proceeds with hydrogenation, but you will have to use greater number of moles for your hydrogen. So for instance, you have your starting material, platinum and hydrogen. Once the hydrogen is added to your alkyne, you will get 1 mole of that hydrogen to your alkyne. You first obtain your alkene. You need another mole of your hydrogen in the presence of your catalyst, of course, and you eliminate your double bond and you actually add 2 hydrogens there. So this kind of reactions, the addition of hydrogen to your alkynes and alkenes is an example of an addition reaction. So it's the opposite of the elimination reaction. The hydrogen actually is being added to your alkynes and alkenes. So again, as I have mentioned, one of the heterogeneous catalysts that permits the hydrogenation of alkyne to an alkene is the use of the nickel bromide. You have here nickel bromide, commonly called as the P2 catalyst. So this is how it's being prepared. You have the nickel acetate here in the presence of sodium borohydride, in the presence of ethanol. This one is being reduced to produce your nickel boride here, or P2. So nickel boride is one of the catalysts that's being used in the hydrogenation reaction to follow the syn addition. So syn addition of your alkyne in the presence of hydrogen and the presence of your nickel boride, okay, you have your P2, actually proceeds with syn addition. So what happens when you have your H2 and you use this catalyst, you actually produce a syn. So you have your hydrogen at the same side. What you get actually is a cis of your alkene here, because there is a syn addition of your hydrogen on the same side. Okay, so cis or Z, 3-hexenes. We start with 3-hexene. We actually reduce this to double bond, and the double bond, the alkene that we obtain actually follows the syn addition if we are using a P2 catalyst. It's a heterogeneous catalyst, the P2 or the nickel boride. Now we can also use what we call as a Lindlar catalyst. Also, it follows the syn addition. The Lindlar's catalyst uses palladium in the presence of calcium carbonate. Okay, and you can also prepare our cis alkenes here. And so metallic palladium deposited on calcium carbonate. You have your palladium deposited on calcium carbonate can be used in this way after it has been conditioned with lead acetate and quinoline. So you have a quinoline is an amine. We'll discuss more of this in chapter 20. So I'm not sure if we can cover that in 131, but in 132 definitely you can cover that one. So anyway, the basic ingredients of the Lindlar catalyst, you have your palladium and calcium carbonate, but just know that this also has been conditioned or has been soaked with lead acetate and quinoline before it's being used as a Lindlar catalyst. The Lindlar catalyst also follows the syn addition. So there are 2 catalysts for your alkynes to proceeds with the syn addition. You have the Lindlar catalyst and you have the P2 catalyst. You have here.